welcome back. It's the last talk of this week. I hope you've all been having a good week. I certainly have been. It's worth noticing that an event like this always takes so much time and energy to organize, and everything has been running so smoothly this week. But you guys have 2 more weeks to look forward to of this. But still, for those of us who are here just for the first week, let's thank the organizers. All right. Just have to get through 1 more hour and then we'll all be free. So I promise I'll try to keep this relatively light. Hopefully, I'll stick to my promise. There is one comment on the feedback form where someone wanted to see my notes. So I did post them at that link over there. I wasn't intending to post them, so they're not very nice. My apologies for that. So, perhaps you will not find them very useful, but just in case you do, they are available. I'm sorry for my handwriting. Anyway, so you will find them there. There are also a couple more homework problems for what I'll talk about today. I'll also be in the tutorial room from 3:30 to 4:30, but maybe today's tutorial session shouldn't be so much about the problems. It can just be about, if you just want to chat about surfaces and four manifolds, feel free to come by. That's often the case in all of these sessions, but today especially, let's try to make it pretty casual. So don't feel like you have to solve problems if you come by at 3:30. All right, so what will we do today? We're going to finish off our uniqueness discussion from Wednesday. I promised you 2 things. I was going to give you a smooth construction and the sketch of a theorem in the topological setting. I'll remind you of what those things are in a second. The first one was about the procedure of rim surgery, and the second was the proof of this Freedman and Quinn theorem about the topological and knotting theorem. So we'll do those. It'll be very sketchy. That'll be fine. And at the end, we'll talk a little bit about the things that I did not talk about, and then maybe we'll have a short summary, and that will be it. So nothing especially scary, nothing especially intense for today. The procedure, so I owed you a smooth construction. So let's start with that. This is a procedure called rim surgery, which is due to Fintuschel and Stern. So this was a procedure where, so I pointed out that we are not so good at detecting exoticity for embeddings of surfaces in S4, but it turns out we are pretty good at it in other four manifolds. And this is the procedure that shows us how to construct them. So here's how this works. So we need a seed surface. So we're going to start off with some sigma inside of a four manifold. Just any old surface. Let's say it's locally flatly embedded. Doesn't have to be smooth if you don't want it to be. And then let's see inside of sigma be an orientation preserving curve. I need one more piece of data. I need K inside of S3, a 1 knot. So here's what this looks like right now. So I have some surface sitting inside of my four manifold in an interesting way. Let me draw it kind of wiggly to depict this. And inside of this surface, I have some circle C. It's orientation preserving, which means it has a neighborhood which looks like an annulus. Right? And on the other hand, I have a knot. Let's say it's this one. It's K. Starting from K, I'm going to build a tangle. So I'm going to build something I'll call K plus. And K plus will be just this knot, except I'm going to cut it at one point, and well, you'll see what I'm going to do. So let's call this thing K plus, and this is sitting inside of B3. Okay. Here is now the procedure of rim surgery. So I'm going to look at a tubular neighborhood of C in M. Let's call it nu C. Now I could consider its intersection with the surface. Well, what is this? This is S1 cross B3. Just because that's a circle inside of a four manifold, let's say it's orientable if you like. So it's an orientation preserving circle inside of the four manifold, and it's orientation preserving inside of sigma. So the intersection with the sigma looks like this. There's this annular neighborhood of that circle there. And what I'll do is, well, there's that interval inside of that B3, but that's an interval inside of B3. So for each of those intervals inside of B3, I take out this straight arc, and I glue in this one instead. Okay, so specifically, I'm going to replace by S1 cross B3, comma, this K plus. So pictorially, what I'm doing is, pictorially on the left here, I had this picture, cross S1. So these horizontal lines are these fibers as I go around this C, right? So each of these orange things, should have kept to my colors. So each of these orange, well, that's not a good color. So let's make this blue. So each of these fibers is just this thing showing up in the B3, and I'm going to replace it by, and again in a copy of B3, like that. Does that make sense? So I chop up my surface right here. I have this, I need to fill in an annulus, and that thing cross S1 is an annulus. It's just a knotted up annulus. I just stick that in there. Has the same boundary, that's why I'm allowed to do it. Okay. This is cross S1, sorry. I should have said cross S1. Does that help? So at each, okay. So I have a blue interval. There's S1's worth of those blue intervals. And each of those blue intervals gets replaced by this tangle. And I go all the way around. It might be helpful to imagine, what if you were doing this to a sphere? And if you did this to a sphere, you'd get the spin of this knot K. So all the way back in our first lecture, we talked about spinning a one knot to get a two knot. And if you were to start with the unknotted two sphere and pick like the equator and you did this operation, you would get that back. But here we're doing this in a more general setting where you just do it to any potentially interesting orientation-preserving circle inside of some embedded surface. Okay. Other questions?
Do you write your maps as maps of pairs to preserve flatness conditions, or is it just
I'm writing it this way, and for a couple, well, I'm not really caring about local flatness or smoothness. I guess if you want to be careful, you should make sure that this, for smoothness, you should make sure that the tangents at this point are kind of lining up correctly or something like that. As always, I am not caring about that at all. I'm just assuming that that can be done. I'm writing it as a pair, kind of to indicate, for one thing, that the ambient manifold is not changing at all. Right? So I'm not changing this S1 cross B3. I'm just in each S1 cross B3, I'm changing the surface, not B3. Exactly the same ambient space, it's just the surface that's changing. Okay. Yes? Sorry? It will depend on some things, that's true. You are making, a priori, it looks like you're making a choice of trivialization, and you should worry about these things, I agree. So at this point, there are many things about this construction that I'm not gonna tell you, and in particular, I won't tell you about these choices of trivializations, but that is something that you should definitely worry about if you were to work with this. Okay. Let's call this result. Sigma sub k comma c. There's an alternative viewpoint. And that's the following. I just wanted to show you this because we saw the rim torus before. So you have this circle C inside of sigma. So you could consider its corresponding rim torus. C cross S1. And remember, what was that? We said, well, this is a surface, sigma, sitting inside of a four manifold, so it has a meridian. At each point, there's a meridian. I just take this C, I take the union of the meridians all the way around this C. To be more precise, I take the normal bundle of sigma restricted to C, and that's C cross D2, and I take the circle fibers there. That's the thing I call the rim torus when we were talking about the Garfoulidis-Teichner Alexander polynomial one-knots or topologically sliced proof. So if you consider that rim torus, you could do the following. You could take your ambient space M, and you can carve out this rim torus cross D2. And then you could glue in, what do I need? Well, this is a torus cross D2, so the boundary is a 3 torus. So I need to glue in something with a 3 torus boundary. So the thing that I will glue in will be S3 minus an open tubular neighborhood of the original knot K cross S1. This has a torus boundary, and that is an S1. So the boundary of this is a 3 torus. So I can glue these things together. Now I need to tell you the maps. So this C is going to be mapped to by that S1. The meridian of K and the longitude of K will get mapped. So mu will get mapped to that S1, and then this will get mapped to that boundary of that D2. Let me put some arrows there. So that one and that one is not so important. I don't want to spend too much time on this. But this might be familiar to you as an operation on a four manifold. This is the Finterschel-Stern knot surgery. And so this procedure, in other words, is the following. Do the Fintuschow-Stern knot surgery on the rim torus. And if you haven't seen this before, don't worry about this too much. It's just something. The point to note is that the rim torus is only interesting with respect to the surface on which it hugs. So if you were to forget sigma, it's just a totally trivial torus. So doing the Fintuschow knot surgery doesn't change anything about that ambient manifold. But you're doing this knot surgery operation in the complement of a surface, so the complement changes. And changing the complement is the same as changing the surface, if that makes some sense to you. Okay? Anyway, this is like a different way of looking at this. This is much more diagrammatic, much more pleasant. This is how you actually prove things, as far as I know. Okay. And I wanted to tell you how this operation produces exotically knotted surfaces inside of Four manifolds. Here's the result for this. Here's how that goes. So let me state the following as a fact, due to Boyer, that if the fundamental group of the complement is trivial, then m comma sigma and m comma sigma kc are homeomorphic, meaning that there's a homeomorphism of m to m taking sigma to sigma kc. It's not quite what I said equivalence of surfaces should be. There should really be something about isotopy. I'm not going to talk more about this. This is also a completely reasonable way to think about equivalence of surfaces. If you're really annoyed, you should think about the mapping class groups of simply connected Four manifolds, where we actually do know quite a bit in the topological setting. Okay? So that's this fact due to Boyer. On the other hand, we have this result of Fintuschow and Stern that says, suppose you have m symplectic, sigma and m also symplectically embedded. Let's assume that m is simply connected and the complement of m is also simply connected. And we're assuming that the genus of sigma is positive and the self-intersection of sigma is non-negative. Then they showed that if there exists a diffeo of m sigma k1c and sigma k2c, then the Alexander polynomials of k1 and k2 have to be equal. So in particular, if you start off with a knot which does not have trivial Alexander polynomial, then you've changed the diffeomorphism type of the surface that you started off with. There is a big difference between this and this. Is that what you mean? These are not contradictory because that is a homeo. But you would only get a homeomorphism. So this is about diffeomorphisms, and that's about homeomorphisms. And so what I'm trying to say is, like, for example, consider M to be the K3 surface, and sigma to be a generic elliptic fiber, it turns out that this is satisfied. And so your surface will be mapped to the rim surgery by a homeomorphism, regardless of k. But all of this is also satisfied, so there will not be a diffeomorphism. And therefore, the surface and its rim-surgered evil twin will be topologically equivalent, but not smoothly equivalent. Does that make sense? So right, so the main thing to highlight is that this is a homeomorphism, whereas this is a diffeomorphism. And this is yet another example of how the smooth and topological settings are so different in dimension 4. Yeah? The thing that I read in their paper said non-negative. And I always interpret that incorrectly, but that's what non-negative should mean, right? I may have transcribed it incorrectly, but I just got it from their paper, so. Let me point out that almost certainly I've made lots of typos everywhere, but it's more there's some result like this which will apply. But please feel free to look that up and then correct me. Yes? Only diffeomorphism. And in fact, there's a later sentence in the Fintelschel-Stern theorem which says that in most cases the resulting surface will not be symplectically embedded, even if the original one was. But let me say right now, I barely know what the word symplectic means, so I don't want to answer more on that, because I can't, just to be clear. Other questions? This was the first operation that was used effectively to create these surfaces that are topologically the same but smoothly different. And since then, there have been lots and lots of modifications of this process. There's, just like we did twist spinning, we did spinning of a 1 knot to produce a 2 knot, and that has been generalized in lots of ways. And similarly, rim surgery has been generalized in lots of ways. There's twist rim surgery, roll twist spin rim surgery, concordance rim surgery, just any word that you can put in the front, there's some sort of rim surgery. And consequently, and that has been applied very effectively to find more and more examples of surfaces that are, in this way, topologically the same but smoothly different. I don't want to talk more about that. You will learn lots and lots about smooth tools and techniques in other mini courses, both this week and next. Okay. And I would rather tell you about the topological thing that I promised I would tell you about. Which was the following theorem of Freedman and Quinn. From 1990, which said that if you have a 2 knot with pi 1 z, then k is the unknot. So it's topologically unknotted. Right, and as a reminder, the smooth analog of this is still open. It's very open, hugely, completely open in every possible way. But topologically, this is the analog of the classical result from 1 knot theory, which does in fact hold in dimension 4, but just in the topological setting. So my plan was to outline this proof for you. I will not go into a lot of details, just to sort of give you a sense of what kinds of tools show up here. The key tool will be the following things. So I enjoyed this. Paulo last in his talk talked about the surgery exact sequence. And I will also use the surgery exact sequence. But a totally different surgery exact sequence. I think mine is the correct one, obviously. But as I mentioned, surgery is like this extremely overused term. As you can see, like we've surgered so many things. This is a different surgery exact sequence. I won't really tell you what it is. I'll just use it. I'll use what goes into it without using any of the words, and the Escobar-Disson theorem. So this one will be implicit, and this one, let me actually state. Let me start off by saying the Escobar-Disson theorem is like one of the pinnacle achievements in manifold topology. So all of you should see it at some point in your life. And maybe all of you have seen it, but I don't want to take that chance. It's the last day. We're just going to state it and like go through what it means a little bit to the extent that we need it. So if you remember nothing from this mini course, maybe you'll remember this, and I will still be very happy. So what is it? So let's talk a little bit about that. So suppose you have a cobordism. So let this be a cobordism. What does that mean? That means the boundary of W is the disjoint union of M0 and M1. Well, we say this is an H cobordism. If the inclusion maps of the boundaries, so let's call them J sub I, going from Mi into W, if these are homotopy equivalences. The H in H cobordism is for homotopy, if you will. So the idea is that a cobordism is sort of like, it's like a cylinder. It wants to be a cylinder, except it's more general than a cylinder. And an H cobordism is like, at least up to these inclusion maps, it's like a cylinder. When I said S here, so I should tell you what an S cobordism is. I'll only tell you very vaguely. The S in S cobordism is for simple homotopy equivalence. So we'll still consider these inclusion maps, but we'll want them to be simple. I don't want to tell you what those are, because all I will ever need are S cobordisms with trivial or infinite cyclic fundamental groups. And so let me just tell you the fact that if pi 1 of W is equal to 1 RZ, then H cobordisms if you have an H cobordism, then it's also an S cobordism. Does that make sense? So simply connected are infinite cyclic pi 1 H cobordisms or S cobordisms. So the letter kind of doesn't matter. Okay. Okay, great. Here's the theorem. It's kind of deceptively simple. Again, Freedman Quinn. Say 80s. This says that if you have a 5-dimensional H cobordism, well, which letter should I use? Let's say H cobordism. With fundamental group either trivial or infinite cyclic. Well, I was saying earlier that an H cobordism is just like up to homotopy, the cobordism looks like a cylinder, and the theorem says it's actually a cylinder. Okay. So then W is homeomorphic, very important, homeomorphic to M0 cross interval. This is extremely important. Let me point at this some more. I only get a homeomorphism, just a homeomorphism, definitely no more than a homeomorphism. Donaldson showed that you don't get a diffeomorphism. Okay. In higher dimensions, there is a fully smooth H cobordism, S cobordism theorem, but in dimension 4, as in for 5-dimensional H and S cobordisms, we don't get it. Okay? Just a homeomorphism. Yes? Notice I did not use that adjective, and that was intentional. So in fact, this could just be a topological, a fully topological H cobordism. Another amazing result of Frank Quinn is he showed that 5 manifolds have topological handle decompositions. So for example, if you know a proof of the H cobordism theorem, chances are it uses handles. And Quinn told you you can use handles in the topological setting. There's a lot more that goes into it, but that might have been something you were worrying about, that you don't have to. Other questions? Have you all seen this before? At least some of you have not seen this before, perhaps. You should see this theorem. It's a big deal. Question?
Just a small technical question. By one who see S cobordism is equivalent to H cobordism because like some white hat group or something,
that's all. So in fact, right, the thing that I chose not to talk about was the white hat group. There's something called a torsion associated to any homotopy equivalence or any H cobordism. And S cobordism is one where that torsion vanishes. That torsion lives in something called the white hat group. And the white hat group of the trivial group happens to be trivial. White hat group of Z happens to be trivial. Many white hat groups happen to be trivial, but not all. For example, Z mod 5. But we don't care about this. We're just going to use these two cases. And if you want to know more, you should. And then please go look somewhere else. Other questions? This is a hugely important result. It's extremely important in classification questions. Okay. If you want to show that two given spaces are not homeomorphic or not diffeomorphic, you cook up some invariant, right? That's fine. We can all try to come up with invariants. But if you're trying to show that two given things are homeomorphic, then what are you going to do? Like, if you could try to write one down, but you don't know your spaces. They're just some spaces. And this gives you a way to sort of get a homeomorphism kind of, I don't want to say for free because there's a difficult theorem, but indirectly it gives you that M0 and M1 are homeomorphic without ever writing down an actual homeomorphism. And so that's just extremely powerful to be able to do that. So that's like, you know, have you ever wanted to write down a homeomorphism directly? No? Then you should like this theorem. Okay. All right. Great. Oh, side note, one of the questions on the homework today is how to use this theorem to prove the topological 4D Poincare conjecture. So in case you weren't convinced that this is a cool theorem, maybe that might convince you. All right, so proof sketch. This will be very sketchy, okay? That is the thing I'm sketching. We'll see how the escabordism theorem comes in, but we'll basically unravel the surgery sequence. The first thing I want to convince you of is the following. Note, it will suffice to prove that this complement of my given 2-0 is homeomorphic to S1 cross D3. It's worth thinking about this for a second. I'm saying if my complement is S1 cross D3, well, then I can plug in an S2 cross D2, and that will be my knot, basically. Another way to think about it is well, you want to show your knot is unknotted. That's the same as showing it's the boundary of a D3. Here are lots of D3s. Use any one of those. Also, you believe this in classical setting as well, that if you know that your complement is S1 cross D2, your classical knot is unknotted. Same proof will work. In fact, works in all higher dimensions. So this one is not unique to dimension 4. Okay? Anyone going to object? Great. OK, cool. Well, now I'm reduced to showing that two spaces are homeomorphic. And look, I have a tool that's going to help me do that. So I need to somehow land in a situation where I have an escabordism, and then I'll win. And so, again, this will be very sketchy. You're trying to show that two spaces are homeomorphic. You're going to use the escabordism theorem. The first thing you should do is show that the space is homotopy equivalent to the one you want. I'm going to call that step 1. That's algebra. You know that pi1 is correct. You have to show that the higher homotopy groups vanish. Higher homotopy groups are a bit scary. In reality, what you do is you show that the homology with twisted coefficients vanishes. That's a different scary word. But people can do this. This is not too difficult. Once you know what all of those words mean, it's not that bad. Suppose you have this. Then you have an actual F that gives a homotopy equivalence. Again, you want an escabordism. Well, the next best thing you might aim for is just any cobordism. Okay? So the next thing will be, if this is your knot complement, just build any cobordism. What am I trying to say? I want there to be an S cobordism between S3 minus S4, between my knot complement and S1 cross D3. But let's try to fit any 5 manifold in there to begin with. And in particular, I could try to build something with a map to S1 cross D3 cross interval, which has my little f on top. Little f was a map from the knot complement to S1 cross D3, let's say cross 1. And on the bottom, I have the identity map. This is a kind of weird thing to try to do. I am aware of this. But suppose you were trying to do this. Well, what do you need to do in order to find such a bordism? finding such a y is equivalent to showing, well, I have this map and this map. I need to show that those two maps are equal in some sort of Bordism group. Okay? So I need to show that this is equal to this in some Bordism group. It's the Bordism group over this space. Specifically, I also need this condition on normal bundles, but don't care about that. The point is, the existence of such a y is a question about Bordism groups, which is a question in homotopy theory. And maybe not all of us in this room, but people know how to solve these questions in homotopy theory. And therefore, this step is also just like, it's doable. It's not, once you know all of the words that do it, you can do it. This turns out to be, this normal Bordism group turns out to be in bijection with certain cohomology classes for these spaces. We already computed what those are. And so you just have to sort of work through these details and you find yourself some y. Yes?
For any cohomology, for example, if y is simply connected, you never should find such a map.
If y is simply connected, I'm trying to find y. What I'm trying to say, I'm not trying to find y and then trying to find an f. I'm trying to find a y which extends little f and the identity. Does that make sense? I know I said that in the wrong order. So I have this map f and this map identity, and I'm trying to find a y that precisely extends. So this exists with the right boundary, and this map exists. So I have to solve both of those problems at the same time. And again, side note, I'm unraveling the surgery exact sequence. These are the steps in the real surgery exact sequence. This is what you do, okay? Okay. Once you have this guy, what you would really, really like, well, I have y, but what I really wanted was an escobordism. Okay. Turns out there is a procedure, again called surgery, which allows me to take some cobordisms and surgery them into escobordisms. Okay? But I can only do this if a certain obstruction vanishes. Okay? So if the surgery obstruction for y vanishes, then can surger, whatever that means, y to an escobordism. The surgery happens in the interior. So this is a big black box for the moment, but do you believe that if I could somehow upgrade this y to an escobordism, then we would be done? Because then I would have a homeomorphism, and that's all I wanted. What this big surgery machine tells you is that if you have such a bordism, again with these conditions on normal bundles that I'm not telling you, if you have such a bordism, then there's a precise obstruction that you can compute such that if that obstruction were 0, then you can jiggle with your cobordism to make it into an escobordism. Then you apply your escobordism theorem, get your homeomorphism, and then you're done. Okay? So let me write step 5. Apply escobordism theorem. And that will end your proof. There's still a step 4 missing, and that is precisely this. The surgery obstruction, well, I got this out of some bordism group magic, and I don't know anything about this obstruction. What I do know is that that obstruction lives in some group which has a name, And I know precisely what that group is. It turns out to be isomorphic to Z. And I know precisely how to realize these obstructions. And so maybe my Y that I started off with has 8 million surgery obstruction. But I know something that gives me surgery obstruction -1. And so I can always take that -1 guy, tack it onto my Y in a way that that surgery obstruction becomes 0. And then my new cobordism, I can then surger into an S cobordism. Then I get my homeomorphism, and then I'm done. Okay? Does that make sense? Yes. Many, many ways. The first and main place where I do this is, well, first of all, the S cobordism theorem doesn't hold in the smooth setting. And what I'm doing is I'm unraveling the surgery exact sequence, and that is not exact in dimension 4 for smooth manifolds either. So this fact that I'm telling you, that if the surgery obstruction vanishes, then you can surger to an S cobordism, that's a fully topological statement. And that is not. Actually, let me take that back. This is a bit confusing because this is a 5-dimensional surgery problem. So 5-dimensional surgery does, in fact, work smoothly. But in order to define the action of this L5 onto these things that I've defined, in order to even have that action, you can only work topologically and not smoothly. My apologies. That was a bit convoluted. But what we're doing is 5-dimensional surgery, but what we're using is the action of this group in the 4-dimensional surgery sequence, because we're working on cobordisms like this rather than closed manifolds. And so even just to define this action, you have to leave the smooth setting. Yeah? I didn't say anything about the fundamental group. I should have said that that Z is the fundamental group. So this is pi1. This is pi1 of W. W? W? What is W? Pi1 of, I guess, this thing. Let me just say pi, because I don't have any space. But like pi of this space. Pi1 of this space is what goes in here. Doesn't matter. So this pi1 does not matter. It's only the pi1 of the target that matters. And in reality, what we do when we do this surgery is we upgrade this map F to a homotopy equivalence. And that's how you kind of know that it's an S cobordism. And that's why you have to work with these maps. And in some sense, what we're doing is you start off with any old map, and you're trying to upgrade it to a homotopy equivalence. Well, you know that a map is a homotopy equivalence between CW complexes if and only if it induces isomorphisms on homotopy groups. And that's what this procedure does, is it checks all of the different homotopy groups and like kills all the kernels. And that's how it upgrades this thing into a homotopy equivalence. Simple homotopy equivalence. Other questions? Yes? I said that pi here, yes, that's right. So this turns out to be 8z, where that's detected by a certain signature.
But didn't you also say that you can realize the generator?
Yes. By generator, I meant 8. Okay. Anyway, it's z, but like if you wanted the actual numbers, it's.
But I mean, why can't you just say, I mean, whatever this group is,
Uh-huh.
or that every element in this group can be realized by some quantity y, I just stack on that,
Mm-hmm.
that y.
That's exactly. Wait. Oh.
You never even need to know what this group is.
So the
Please go on.
the realization problem is every element of this group is realized by a map from a 5 manifold to S1 cross S4. But you're not looking for a map to S1 cross S4. You have a certain boundary condition that you want to maintain. So you take the generators of this thing, and you tack it on in the interior of this guy. The main point is like you are really interested in the boundary, but these generators are like realized by closed maps of closed things. And the modification you'll do will be in the interior. It depends how much you want to black box. You could black box this entire thing to say there's a machine that produces an escobordism. But I'm just trying to open it a little bit, but not too much. Yes?
Yeah, in the notes you provided, you've written down what the 5 manifold that map is from, but I can't quite read.
I don't remember. Can I tell you later? Okay. I have 7 minutes. So with that information in mind, any questions? Okay. So just to recap, got a homotopy equivalence, used bordism theory to get some cobordism, satisfying some conditions. Turns out that there's some number I can compute such that if the number were 0, then I could change my cobordism to an escobordism. But the actual number may not be 0, but because I know precisely what this group is, I can modify my y somehow. Turns out S1 cross E8, if that helps. I can modify this y by changing it using these generators in such a way so that the new thing I get does have trivial obstruction. Then I can surger to be an escobordism, and then I'm done. Okay. So I'm going to very quickly try to write that down. Modify y to a cobordism with vanishing surgery obstruction. Then surger. Then get escobordism theorem, and then you're done. Hey, I only have 5 minutes, so I don't want to write anything down or anything like that. I just want to just immediately go into the summary component. Let me say just like 2 sentences on what I skipped. The 2 things I would have talked about, had I done all of this like twice as fast, are other equivalence relations, are 4 types of equivalence relations on surfaces. The first is concordance. So just like we have concordance of classical knots, you can also consider concordance of 2-dimensional surfaces in arbitrary 4 manifolds and 4 manifolds cross I. It turns out that every 2 knot in S4 is slice. That's pretty cool. But we have no idea if every 2 link is slice. So that's a big open question about concordance of knotted surfaces. There, now I've told you. The second thing I wanted to say is something that people study a lot is, well, it turns out that, okay, you have a surface inside of a 4 manifold. You can consider modifying it, those surfaces. So for example, you could take your surface and change your ambient manifold by connect summing S2 cross S2s. And it turns out that in some situations, surfaces might become isotopic when you do this sort of external stabilization. Or you can modify your surfaces by like adding handles and tubes in some way. There are various flavors of this stabilization operations, and that's another thing people study as well. I'm sorry I didn't get to tell you more about that. You'll find a little bit more in the notes in case that helps. Happy to talk more about this in the tutorial as well. What did we do in these 4 lectures? We've been together for 5 hours now, minus 3 minutes, plus all of the time I've gone over time. There are a few things that I'd like you to take away from these lectures, and instead of just letting you do it, I thought I should just tell you what I hope they are. Some of you are maybe seeing surfaces in four manifolds for the first time. So I hope you'll see that there are like lots of different techniques that are used in this area. There's a lot of different potential for different things being applied. Perhaps you saw that the topological things and the smooth things have very different flavors. There's room here for people to do things that are very explicit, very diagrammatic, very sort of picture focused. There's also places where we do a lot of algebra, lots of things from homotopy theory, lots of things sort of inspired by high dimensions. That's sort of the flavor of like the purely topological surface people, like me. We are often inspired by high dimensional topology. And that's sort of like, one of the slogans is that topological four manifolds, locally flat surfaces, they're just like surfaces or high dimensional manifolds regardless of category. And in that sense, we sort of get a lot of inspiration from there. But dimension 4 is also much nicer. It's not just that, oh, we have all this high dimensional stuff, let's just apply it in dimension 4. I mean, in high dimensions, you don't get to do all these pictures. You don't get to be as geometric. Things become a lot more abstract. So it's not just that we're using all this high dimensional stuff. We're lucky because we also get to draw these pictures. We're like low enough dimensions that this geometric insight is still helpful and applicable. And in some situations, as we saw with these normal bundles and so forth, dimension 4 is in many ways better than high dimensions as well. So if there's one thing I would like you to take away from these lectures, of course, there's the smooth side of the story. You'll hear about smooth things in lots of other places, not from me so much because I'm not that smooth a person. There's lots of really cool open problems left for people to attack, also in the topological setting. Lots of people working on interesting problems still, and maybe you will be one of them. That would be really great. Thank you for joining me. See you maybe at the tutorial session. Thanks.